Hello, welcome to a lesson on binomial expansion. Now, you may not know what this means exactly, but you normally see it in a form like this, where they tell you to expand x plus 3 or x plus 7 or something in this sort. Okay, so there are many different methods in which you can use to work out something like this. The first method that I tend to use is the FOIL method. FOIL. The F stands for first, the O stands for outer, the I stands for inner, and the L stands for latter. Okay, so what that basically means is you look at the first terms in each bracket, you take them and then you multiply them. Then you look at the terms that are the outer, well, those that are more towards the ends of the brackets. So this x there and this 7. And then you take them and you multiply them. Then you go to the terms that are more to in the center, when they're in the middle of the brackets, which are 3 and x. Then you multiply them. And finally, the terms that are last in the brackets, the latter. So that's 3 and that's 7, the last two. So first, the first terms of each bracket, x times x, and then the outer, x times 7, then the inner, 3 times x, and the latter, 3 times 7. That's what the FOIL method is about. So when we use this method, we'll realize that this becomes, the first is x times x, x squared, outer, x times 7, 7x, inner, 3 times x, 3x, and latter, 3 times 7, 21. And finally, after some simplification, you can simplify the 7x and the 3x together and add them. So we get x squared plus 10x plus 21. We don't add these two because all of these now are unlike terms. The only like terms we had were the 7x and the 3x because both of them included an x. Okay. Now there is another way that we can expand this there. I'll show it just now. The other method that we can use to expand x plus 3 by x plus 7 or something that is similar to that is simply multiplying each term in the bracket by everything, basically distributing it completely with everything. Let me show you what I mean by that. So you take in the x, then you multiply it by x. You take in the x again, and then you multiply it by the 7. Here you take the 3 now, you multiply it by x, and you take the 3, and then you multiply it by 7. So you multiply x by everything in that bracket, and then you multiplying 3 by everything in that bracket, basically. So when you do x times x, we get x squared. X times 7 is 7x. 3 times x, 3x, and 3 times 7 is 21. Simplify this, our like terms, 7x and 3x, when you add them we get 10x. So that's x squared plus 10x plus 21. Now if you look at this, this is basically the same as our FOIL method. Taking the two terms in the first bracket and multiplying it by each in the second is the same as a FOIL, because x times x are the first, x times 7, that's the outer, 3 times x, inner, 3 times 7, latter. So it's the same as the FOIL method. Now, there are also more creative and fun ways in expanding this. So what we have there, we have a rectangle. And the distance from there to there in our rectangle is x centimeters. We're using x because we didn't actually measure it. And the distance from there to there, we know is 3 centimeters because we actually measured it to be 3 centimeters. Okay. Also, the distance from there to there is x centimeters, and the distance from there to there is 7 centimeters. We didn't measure that distance. As far as we know, it can be anything because we didn't measure it. So we're just going to give it a variable to represent its value. Yes. So we can use this in order to expand the same thing, but let's see how. Now, all rectangles has 2 widths and 2 lengths. The widths are the same. The widths are the same length, and as well as the lengths, they have the same length. If you measure the distance from there to there, it should be equal to the distance from there to there. Likewise, distance from there to there should be equal to the distance from there to there, because that's what a rectangle is essentially. So if we look at the width of this rectangle, if the distance from there to there is x and the distance from there to there is 3, that means its width, we represent the width by w, should be equal to the sum of the 2 distances, right? So x plus 3. Likewise, if we want to find the length is the longest side of the rectangle. If the distance from there to there is x and the distance from there to there is 7, then the total length now, we'll call it capital L, is equal to the sum of the 2 distances, x plus 7. We'll leave it as this because x and 3 are unlike terms. X is a variable, 3 is a constant. Okay, so we know the width is x plus 3 and the length is x plus 7. But what about the area? What about the area of this rectangle? Now, area, I'll represent it by A, capital A, is equal to the length multiplied by the width, or is the same as the width multiplied by the length. The commutative law says that you can change the order for multiplication and the answer will not change. So length times width is the same as width times length. It doesn't matter. So what that means is that the area of this rectangle is equal to x plus 3 by x plus 7. Binomial expansion, right? Okay. Now let us expand this in a more creative and intuitive way. Let us say we divide this rectangle into 4 smaller pieces. 4 smaller rectangles, I should say. Okay, so we have separated our rectangle into 4 smaller pieces. So this first piece, we call it A, we call this one B, we call this one C, and we call this one D. Now, since these pieces came from our large rectangle, it is important to realize that if we take the areas of each of these and we sum them up, it should be the same as the area of our entire rectangle, because we took our rectangle and we divided it into these pieces there. So if we sum up the areas of these pieces, it should be the same as the area of the entire rectangle. Okay, so that means the area should be equal to the area of the entire rectangle should be equal to the area of A plus the area of B plus the area of C plus the area of D. So that means that when we expand x plus 3 by x plus 7, That should be equal to the area of A plus the area of B plus the area of C plus the area of D. All right. So now, what is the area? What is the area of A? So this is A there. A is actually a square. Its length is x centimeters and its width is x centimeters. These two lengths are the same. This is why it's a square. So the area of A, length times width, is x times x. That is x squared. Now what is the area of B? The length of B is 7. As you can see, the width of B is x, because if there is x, there have to be x as well, right? So that means the area of B is 7 times x. 7 times x is now what? 7x. What is the area of C now? The width of C is 3. The length of C is x. So the area of C is 3 times x, which is 3x. And what about D? The length of D is 7, because if there is 7, there should be 7 as well. And the width of D is 3. So now 7, the area of D is 7 times 3. 7 times 3 is 21. So we basically break up this entire rectangle, which has a width of x plus 3 and a length of x plus 7, into 4 smaller rectangles, and we said that the area of the big rectangle should be the same as, which is this, should be the same as the sum of the areas of all smaller fragments. So that means the area of the bigger rectangle, x plus 3 width times x plus 7, is equal to the area of A, x times x, x squared, plus the area of B, 7 times x, 7x, plus the area of C, 3 times x, 3x, plus the area of D, 7 times 3 is 21. Now we know that we have like terms there, and we can add our like terms. So we have 7x plus 3x, which is 10x. So this is equal to x squared plus 10x plus 21. You got the same answer. Okay, so the final way of expanding this is actually using the concept of distributive law. Now, before we go into this, I first want you to accept something that is very critical if you want to really understand mathematics. It's a fact that we could have more than one things and treat it as though it is a single thing. For example, we have, let's say, this pen. Now this pen, we consider this pen as just a single pen, but this pen actually consists of parts that each can be considered as a single thing. So this single pen can be broken down into a cap with ink. The ink contains a pointer and a capsule for the ink, the tube I should say. It also contains the case and this end part there where the point comes out from. So a single pen contains these many parts, but we do not treat these parts when they are together as though it's 4 different things. We treat it as one pen. So when they come together, we just treat them as one pen, a single pen. Although it consists of many parts that are different, we just look at it as one pen. This marker, for example, contains a cover, it contains the ink inside as well, and it contains a case. It's one marker, but it's a combination of many different parts. It's calculator, a cover as well. It has many buttons. It has a battery. It has a solar panel. It has a screen. It has so many different things inside, but it's just one calculator. So the same concept can be applied in mathematics, because a pen is essentially a group of many things. It contains the ink, it contains the case, and probably a tube and a pointer. Call that pointer P1. Right? It's one pen, but that one pen consists of many parts, consists of 4 parts: the ink, the case, the tube, and the pointer. A calculator consists of, let's see, I don't want to count it, but let's just say about 20 buttons. It contains the back cover. I'll call the back cover B. It contains the circuit board. I'll call the circuit board the M for motherboard instead, because I don't want to use the same C. It contains many different parts. So, but basically all these parts, when they are together, they are one thing. So we can apply the same principle in this case. Let's see how. Okay, so before we continue expanding this, I want to do a quick review of the distributive law. So remember the last time in the previous video we said that we have some, let's say, some number or letter on the outside of the brackets, and then we have the sum of terms inside, x plus y. So the distributive law says that you take what's on the outside and then you multiply it by everything that is inside. So that becomes 2x plus 2y. Same concept. If you have p on the outside, and then we have, let's say, x plus 7, we take what's on the outside and you multiply it by everything inside. So that's px, and p times 7 is 7p. Okay, so now back to this. So now we have x plus 3 and we have x plus 7, and we want to use the concept of distributive law to expand this. Now, as I said before, we could have two separate things together. We have the x here and we have the 7, right? That's two separate things, but we can treat them as though they are one. The same way we had 4 different components that make up one pen, we can have 2 different fruits in one package, like like an apple and a banana in one package. The package is one, but it has two components in it. So we're treating the apple and the banana as though it is one. A calculator has many different parts, but you do not look at the calculator as a combination of many different parts. We look at the calculator as a calculator, a combination of many different things. We look at it as this is one. So the same way, you can look at the x and the 3 as a single package. We can just look at it like a single number. So the same way you would look at this as though p is 1, I want you to look at x plus 3 as though x plus 3 is one thing, as if it's one letter. Just pretend it's one thing, like p. So if you pretend that it is 1, if you're following this, we take what's on the outside, in case it's that, and then we multiply it by everything. So that's p times x and p times 7 But in this case, we're treating this as though it's one thing. So now it's x plus 3, what's on the outside of this bracket, by 7, and x plus 3 by x, and x plus 3 by 7. So we're treating x plus 3 as though it is one thing. So that becomes x plus 3 by x is equal to x by x plus 3. And x plus 3 by 7 is equal to 7 by x plus 3. Right? And now we can use distributive law again, because we have brackets and we have something outside. Same thing for the brackets and some term outside. So this is x by x plus 3. We take what's on the outside and multiply it by everything inside. So that's x times x squared, x times 3, 3x, and this one we put back the plus that was there, 7 times x, 7x, and 7 times 3 is 21. So this becomes x squared plus 10x plus 21. All we did, we just pretended that the x plus 3 is like a single letter, as so it is like p. So we just pretend as if it's one thing. So we take it and we multiply it by everything inside of this bracket. So x plus 3 by x is this, and x plus 3 by 7 is this. So now we have two different things that we can use distributive law on: x by x plus 3 and x 7 by x plus 3. So x by x plus 3 is x times x squared, and x times 3 is 3x, and 7 times x is 7x, 7 times 3 is 21. And then when you simplify the like terms, we get this. So these are the different ways that you can do binomial expansion, but it's up to you to choose the one that you prefer the most. Okay, so now I have a list of different things that I want to expand by binomial expansion, and I'm going to try to use some of the same methods that we talked about before. Okay, so the first one, we have x plus 4 by x minus 2, and I'm going to use the FOIL method to expand this. I'm going to do that there. So x plus 4 by x minus 2. You're going to use the FOIL method. So the F stands for first. So we take in the first terms in the two brackets. So the first term in this bracket is x, and the first term in this bracket there is x. So we take in these two and then we multiply them by each other. So x times x is x squared. Then those on the outside or towards the ends of the brackets. So the outer, those towards the ends, x and negative 2. So we go x times negative 2, which is minus 2x. Then the inner, the I stands for inner, the 4 and the x. These are more towards the inside because they are more inside than any others. So they are referred to as the inner. So that's 4, and the x, we take them and we multiply them. 4 times x is 4x. And then finally the latter. Those are the last in the brackets. So the 4 is last and the negative 2 is last. So we take in the 4 and the negative 2 and we multiply them. So 4 times negative 2 is negative 8. Okay, simplify our items. We have minus 2x plus 4x, and that is positive 2x. So that becomes x squared plus 2x minus 8. Okay, so the second one, we have 2x plus 1 multiplied by 3 plus x. So the method we are going to use this time is just distribute everything everywhere. That's how I like to say. So you just multiply everything in that bracket by everything in this bracket. So that's 2x times 3, and then 2x times x, and then 1 times 3, and then 1 times x. So 2x times 3 gives us 6x. Then we do 2x times x, that gives us 2x squared. And now 1 times 3 gives us 3, and 1 times x gives us x. So our like terms there are 6x and x. So this becomes, I'm going to start with the 2x squared first, because it doesn't matter which order I put it in. So that's 2x squared. 6x times x is 6x plus x, sorry, is 7x. And then finally our plus 3. So for number 3, going to go back to our FOIL method. Number 3, we have 2x plus 6 by 2x minus 6. FOIL method says first, outer, inner, latter. So our first of each bracket are these two, 2x and 2x. They come first in our brackets. So 2x times 2x is 4x squared. Then our outer, those are more towards the end. That's 2x and negative 6. 2x times negative 6 is minus 12x. So our inner now, those that are towards the middle or the center, 6 and 2x. 6 times 2x is 12x. And our latter, 6 and negative 6. When you multiply them, 6 times negative 6, that is negative 36. So when you simplify this, our like terms are negative 12x and 12x. These are additive inverses of each other. So that means that when you add them, you get your identity element, which is 0. So basically they cancel out. That's a fancy way of saying that they cancel out. So that's 4x squared minus 36. That's what it becomes. Okay, so finally number 4, I'm going to use the distributive property to expand it. So we're going to use the fact that we can pretend that these two terms can be reduced to a single thing. So you can just pretend that this is actually 1. So we're going to treat this as though it's one thing, as though if it's just one letter or one number. And then we're going to take it, and then we're going to multiply it by everything in the other brackets. So now we have 5b plus a times b. That's just basically b times 5b plus a. And then we have 5b plus a times negative a. It's basically a times 5b plus a. And now we can use distributive law again in this. So b is on the outside of the brackets, and we have minus a on the outside. So we're going to multiply it by our b by everything inside this bracket, and then we're going to multiply our a by everything outside of this bracket. So we have b times 5b, that's 5b squared, b times a plus ba. A times negative a times 5b, that's negative 5ba, and negative a times negative a, that is negative a squared. Now our like terms there are ba and negative 5ba. So we can simplify them to give us 5b squared minus 4ba minus a squared. Now, it might not be obvious that these two are unlike terms, but like I said earlier, you can treat two things as though it is one. So you can treat the b and the a as though it is one, as though it is one thing. So let's see, b and a comes together to make what can it make? Let's say a pencil. So you take a b and you take a and you put them together to make a pencil. So that means if this is a pencil, then this is a pencil as well. So these two terms are like because both of them will be pencils. Or since both of them contains ba, they are like terms. So you can subtract them. These two are not like terms because this is a and this is b. Two different variables. Neither is this and this because this contains a and this contains this doesn't contain a. Also this contains a square, this doesn't contain square. So these are unlike terms. But these two are like terms because both of them contains ba. So it's ba minus 5b, that's basically 1 minus 5, which is negative 4ba. That's 5b squared minus 4ba minus a squared. Now for the last one, number 5 says that we have, I decided to put this special case deliberately. We'll see why. Okay, so I'm going to use the same distributive property. We're going to pretend that 7 plus 3 is 1. And actually 7 plus 3, we can write it as 1, which is 10. But we're not going to do it. We're going to pretend that we cannot simplify 7 plus 3 and just treat 7 plus 3 as 1. So that's what's on the outside of, we take this and then we multiply it by these brackets. So we're treating 7 plus 3 as 1 with 10. So this is 7 plus 3 or 10 times 8. That's 8 by 7 plus 3 or 8 times 10, that's the same thing. And then we go 7 plus 3 by negative 5. So that's 10 by negative 5 or negative 5 by 10. 7 plus 3. And then distributive law again. Take what's on the outside, we multiply it by everything inside. Same for there. So that's 8 times 7 is 56. 8 times 3 is 24. And you have minus 5 times 7, minus 45. And minus 5 times 3, minus 15. So when you simplify this, 4 and 6 gives us 0, 80. And when you simplify this, 5 and 5 minus, okay, so this becomes 50. So that's 80 minus 50, and that is 30. So let us see if this is accurate, because in fact we can actually use bomb dash or BODMAS for this. This is there is actually an operation that is hidden there, the multiplication operation. We don't write it in these cases, but it's actually there. So we can do the brackets first. So that bracket says, so this is the same as 7 plus 3, which is 10 by multiplied by 8 minus 5, which is 3. 10 times 3 is 30. Notice we get the same answer, because if we got the same answer by using two different methods, it means that both methods, or the method that we are using there, is mathematically sound and it's correct.